So, welcome to our next video. In this video, we're going to talk about basicity and amines. So, amines are known as the official organic base. As you can see from carboxylic acids, they do acid-base reactions fairly easily. And we're going to talk about 4 different factors that influence basicity. So, number 1 is substitution. So, what I mean by that is more methyl groups, more methyl/alkyl groups means more basic. Because remember, alkyl groups, these are electron pushing groups, which is why a tertiary carbocation is more stable than a secondary, because here the methyl groups are donating electrons to help stabilize the carbocation. So remember, in basicity, the lone pairs are the ones that are being influenced. So here, we're trying to make the lone pairs as electron-rich as possible, and that will give us a good base. So pause the video and rank these amines in order of basicity, with 1 being the greatest base. So hopefully you did that, and now we're going to rank them. This one is 1, 2, 3, 4. And the reason being, these has the most methyl groups. So we have these 3 methyl groups that are pushing electrons towards this lone pair. More basic. And then the rest of them have less methyl groups, so naturally they'll be a weaker base. All right, and so the second factor is resonance. So here, let's take why the amine nitrogen is more basic than the N, right? So here, for a good base, we want a rich lone pair. So we want the lone pair to be electron rich and localized. So delocalization resonance drops basicity. So here, these lone pairs on the nitrogen are involved in something else, right? They're involved in resonance. So if they have 2 jobs, they can't focus on one job. So that's why we see the oxygen being protonated, never the N, because the oxygen is supporting, or the nitrogen is supporting the oxygen. Whereas here, these lone pairs, they aren't doing anything, so they're free to react as a base. So knowing that, NH2 versus H. So pause the video and circle which one is the better base. So hopefully you did that, and let's look. So here, this has no resonance whatsoever. So okay, that could be so that's a great candidate so far. So let's look at the second molecule. Here I noticed something. These lone pairs can do resonance, right? And actually this molecule is aromatic. If it follows Huckel's rule, and these electrons are free flowing inside the ring, and if you look here, these lone pairs are involved in resonance. So this one is a stronger base. The next factor is induction. Or actually no, let's cover this with benzenes. So Nasiri likes to ask questions where she has a benzene, and then you have substituents affecting the benzene. So hopefully you still remember your electron pushing and electron withdrawing groups from the first midterm, right? So here we have an oxygen, we have a nitro group, and we just have a regular benzene. So let's look at all three structures. Remember, the oxygen group is electron pushing, and if it's an orthopara to the carboxylate, it can donate electrons by resonance. So here we can draw a resonance structure where there's a negative charge on the carboxylate. So that charge increases electron density. Increase E density, therefore more basic. So, and if we go to the next one, remember nitro groups are electron withdrawing. So what's going to happen here is we can draw a resonance structure where now, instead of that, we have a positive charge. So drawing that out, O minus, plus. But for here, we have part decrease electron density. The positive charge pulls away electrons from the carboxylate. And if it pulls away electrons from the carboxylate, it makes it less electron dense. It makes it a worse base. Worse base. And this one is smack dab in the middle. So for basicity, this one would be number 1. It's the most electron rich. This one would be number 2. There's nothing wrong with it, nothing affecting the substituents. And this one would be number 3. The positive charge pulls electrons away, and it makes it a better acid, but a worse base. And the last thing I'm going to talk about in this video is induction. Remember, NH2 with fluorine versus NH2 and then NH2 with, I don't know, hydroxy. So remember, fluorine, F is very electronegative. So if it's electronegative, what do you think it's going to do? It's going to pull electron density away from the lone pairs. And same thing with oxygen. However, oxygen isn't as electronegative as fluorine, so it pulls less. So if fluorine is pulling away electrons, it makes less basic, right? And then the amine with nothing pulling on it would be number 1. This hydroxy would be number 2 because oxygen doesn't pull electrons as hard as fluorine. And this one would be the worst base. And that's all for today's video. I'm going to make up some practice questions, and that'll be all.